Okay, so we are now going to apply the same. We are going to use the same question as we did for MRS. We are going to find its utility maximization using the Lagrangian approach. So let me pick one on the Lagrangian approach. The Lagrangian approach is very simple. It adds the utility function, this one, to the income function, then introduce a multiplier to the income function. So you have something called a Lagrange multiplier. So with the Lagrange approach, so I'm using the Lagrangian approach. So it says that now I have L. So L will be equal to, we add this to this, but adding this, we don't write I equal to this. We now will send this one here and make it equal to 0. So something like when I bring this one here, I have I minus bx minus by y. That's what we put in. And we introduce a multiplier. So the Lagrangian will be x alpha y beta plus the Lagrangian multiplier lambda multiplying I minus bx x minus by y. So this is the Lagrangian function. So we use the utility and the subject constant or budget constant, sorry. So with the Lagrangian approach, when we want to find a Marshallian demand function, what we need is Lx, that is differentiating this function with respect to x, then Ly, differentiating the same function with respect to y, then L lambda, differentiating the same function with respect to lambda. But we assume that all of them should be equal to 0. Okay. So now having this, we can expand so that we can simply differentiate. So L, when I expand, I have alpha x alpha y beta plus lambda I minus lambda px x minus lambda py y. If you are a good mathematician, you can skip this simplification and just be differentiating straight from this point. But if you are not, you have to save yourself from a lot of danger. So you just expand. So now we find Lx. So Lx is the derivative of this L with respect to x. So now all the other variables without x will be treated as constant. So this will be seen as constant, this will be seen as constant because there is no x. Differentiation of a constant is 0. So now we differentiate this with respect to x. I will have alpha x alpha minus 1, then y beta, plus this goes to 0, and I have minus lambda dx and minus 0 because this was a constant. Differentiation of a constant is 0. We said that it should be equal to 0, so I have equal to 0. So this is equal to 0. So I have alpha x alpha minus 1 y beta minus lambda px is equal to 0. I have alpha x y beta equal to lambda px. Let this be equation 1. Then I'll come and find Ly, which is derivative of the Lagrangian function with respect to y. So this is what I'm differentiating, this one. So with respect to y, I'll have beta x alpha y beta minus 1 plus 0 minus lambda py. That's also equal to 0. When I do the skip steps and bring this one here, I have beta x alpha y beta minus 1 equal to lambda py equal to, that will be equation 2. So I'll try and write that one also. So alpha x, then this beta equal to lambda, yes, that is 1, then beta x alpha y beta minus 1 equals to lambda by 2. Now I have to differentiate with respect to lambda. So differentiating with respect to lambda and equating to 0. L lambda is derivative of L with respect to lambda, which equals, this one goes to 0 because there is no lambda here. We have 0 plus, there is lambda here. So the I, so plus I minus bxx minus byy, we said it should be equal to 0. When we equate it to 0, we get back the income function. So I have I equal to bxx plus byy. That should be my equation 3. Now with this equation 1 and 2, what we are supposed to do is divide equation 2 by equation 1. You can do it opposite. You can do it equation 1 by equation 2. So let me do it even equation 1 divided by equation 2. When I do that, I'll have alpha x alpha minus 1 y beta equal to lambda bx divided by beta x alpha y beta minus 1 over lambda py. This lambda will cancel this lambda, just as we did in the MRS video or MRS class. We will split this, write it as this, so that we can simply apply our indices. So we have px over py. Then with this, according to indices, this, when it comes up, it becomes negative. You can also bring this down. So let's maintain the alpha. So our x alpha minus 1 minus alpha times y beta minus beta plus 1 equal to px over py. And I'll get alpha over beta x. This one cancels this one cancels this. Minus 1 goes y1 goes to px over py. This gives me alpha 1 over beta x equal to px over py. We can now try and make y the subject. When I make y the subject, the MRS approach goes through that we break down. So we get y equal to beta px x over alpha py. So we'll put this equation 4. Now put equation 4 into equation 3. So in place of y, we put the whole thing here. So that I have I equal to px plus py into brackets beta px x over alpha py. This py cancels this py. Then I have alpha here. So I'll try and get rid of this alpha by multiplying the whole equation by alpha. So I'll have alpha I equal to px alpha px x plus beta px x. Now px and px are the same. So it means that I can add the coefficients. So I have alpha I equal to alpha plus beta px x. But alpha plus beta is equal to 1, which will imply that alpha I is equal to px x. Making x the subject, you have x equal to alpha I over px. So that becomes the Marshallian demand function for x using the Lagrangian approach. It was the same thing we got for Marshallian, the MRS approach. It should be the same whether you use the Lagrangian or MRS. It should not be similar. It should not be similar. It should be the same, whatever approach you use. So I'll put this Marshallian demand function for x into the y. So I'll now have y equal to beta over alpha px over py then times x times this x So I'll have alpha I over bx. This bx cancels this bx, this alpha cancels this alpha. I have y equal to beta over py, or let's say beta I all over py. So this becomes the Marshallian demand function for commodity Y using the Lagrange approach, having given you the Douglas function. So if it is about the sales function or Longtiev or fixed proportion, it's all about how to differentiate. So if your differentiation is good, you should be able to try with the other functions. So that will be the end of the utility maximization of Marshallian demand function for commodity X and Y.